Hello, it's Keith here, and this is lesson 4 of my Z80 assembly tutorials. So we had a look last week at a calculator program that was half basic and half assembly, and that was quite a functional little program. But this week we're going to take a step back and we're going to have a look at some more theoretical stuff, and possibly the programs aren't going to be quite so useful. But the reason for that is that I want to cover a lot more commands this week, because although we've done a few interesting things, there's a lot of very important commands we've not covered at all yet. So I want to try and get them in now so we can move on to more serious programming as quickly as we can. So let's have a look at what we're going to do today. So the first thing we're going to cover is a thing called the stack. Now you may remember from what I mentioned before, if we have a look at our debugger here, if we just load that up, the Z80 does not have very many registers available to us, and what's worse, the vast majority of the commands use either the accumulator or the HL register pair, which have more functionality than the other registers. So quite often we're going to be in a situation where we don't have enough registers to do what we want, and we need to use them for something else, but we need the same values that we've got in those registers later for another purpose or for the same purpose again. So we'll have times where we've not got enough registers and we need to find a solution to that. So that's what we're going to have a look at today, and let's make a start. So if I just minimize these two here, and I will get my assembler window in screen here. Okay, and we'll create a new program. So I'm going to just go ahead and start typing in here. And I'll explain what it does as I go along. Now, I'm going to be doing a little bit of cut and pasting this week because there's some more difficult commands and there's quite a lot of code I'm going to be entering this week, but I will explain everything that I put in. So let's make a start. Now, the first thing we're going to do is we're going to copy in a command, and we're defining a symbol, and we're saying that the command printchar is equal to, and then the address BB5A. Now, this is an address in the Amstrad CPC firmware, and if you can't guess from the title, what it does is it takes the accumulator and it prints it as an ASCII character on screen. Now, if you're not familiar with ASCII, I will just explain it to you, and I'll show you on the cheat sheet. If you look here, you can see the ASCII character map as the Amstrad CPC and practically every other system, certainly every Z80 system I'll ever be discussing. They all use the same ASCII character set, at least up to 128. So you can see here A is equal to 65 in decimal or 41 in hexadecimal. Every letter has a different ASCII character, and ASCII stands for American Character Standard Institute or something. It's a standard, so if it's ASCII, it's always going to be the same, at least up to 128. Things like Russian, Japanese will be different, but up A to Z, capital, lowercase, you can be sure it's going to be the same. So anyway, the A is treated as a ASCII character, and it's printed to the screen with this printchar routine in the Amstrad CPC firmware. So we're going to use that to do a little bit of work for us, and it's going to allow us to actually get things onto the screen and not use BASIC this week. So that's what we're going to use, and also we're going to use another command called waitchar. And what this does is it waits for the user to press a key, and then it returns that key as an ASCII character. So using these two firmware functions in the Amstrad CPC this week to do our little program. So let's make a start, and then we're going to start at org and 8000 as we usually do. And what we're going to do is we're going to do call waitchar, and then we're going to do call printchar. So we've asked we're going to take a character from the user puts a key, and then we'll show it straight back to them. And now what we want to do is we're going to, let's think how I'll do this. What I'm going to do first, I'm going to show you a little example, is I'm going to create a temp variable. So temp db0. So all we've done is we've declared a label, temp, and we've put a 0 in it. That's 1 byte, of course. So what we're going to do is we want to store the character the user who has entered into temp. So it's ld temp, A. And then what we're going to do is we're going to do LDA, and then I'm going to put a bar symbol. And you'll see I've put it in these little quotes here, and you might be thinking, well, A needs a number, and that's a letter. That's not a number. Well, what's that mean? And it's quite simple, really. The assembler knows that that character is character 124, so when we compile this it will put 124 into A. It can work it out for us. So just for convenience, just so you can see what we're doing, I can put that in, but I could equally put the ASCII character code in instead. It would function exactly the same. So let's get on. And what we're going to do next is we're going to need another temp variable called temp2. And what we're going to do is we're going to load temp2, A. And then what we're going to do next is we're going to load A, X. I missed a command, I apologise. Retyping a program I've already written, of course, here. So we're going to print the bar onto screen, then we're going to load X, and then we're going to print that onto screen. And then what we're going to do is we're going to load temp2 load, sorry, the wrong way around. We're going to load A from temp2, getting back the character we had before. And then we're going to call print char again. And then what we're going to do is we're going to load the first temp variable, and we're going to print char again. And then we're going to return to basic. So let me double check. Right, that's right. Return, not rent. There is no command called rent. So we'll just assemble that, and we get no errors. I'll just bring that into. And now the system pauses, and it's waiting for us to enter a key. So I'm just going to press the A key, and you'll see what we've got is an A, followed by a bar, followed by an X, followed by a bar, and followed by an A. And let's have a look at our code, and hopefully it's pretty simple to see why that is. We stored the A, the user entered the key there, we print it, we then store it into temp, we then set A to the bar symbol, print that, store the bar symbol, print the X, get the bar symbol back, and get the key the user pressed back. Now, you're probably thinking, what's the point of this? Well, absolutely nothing. It's just a little example that I'm going to use to show you something later. And of course, because we're storing this, if we change this first bar to a colon, a semicolon, for example, and reassemble, and we'll just run this again. You see, they both change because, of course, it's storing it in between. Now, let's have a look at this program here. And you'll see this ends at 8024. So we'll just make a note of that in our little notepad here. So that's how many bytes. So that's how many bytes our little program has needed. So the thing I wanted to show you today is we've used these two temporary variables here to store the numbers we needed, but that's a little bit inefficient, and there is a better way we can do this, and that's using something called the stack. So if I just I'm just going to reorganize this a little bit to make it clear what I do next. This looks right. Okay, so I'll explain what the stack is. Basically, if you think of our little notepad here, if the stack is a temporary storage for numbers for any kind of hexadecimal bytes from within the assembler. It works in 16 bits, and what you do is it's what's called a last in first out stack. And if you think of an in tray in an office, and you can put bits of paper with the 16-bit numbers in that in tray, but you can only ever take the one off the top. You can't go sort of fumbling around and get one from the middle or the bottom. You have to take the one from the top, and that's how the stack works. So if you think of sort of this screen on the notepad as the stack, and you imagine that that line is the bottom of the stack, if I push the number 0001 in, 0001, that will be the first item on the stack. If I push in 0005, that will now be the first item on the stack. And then when I come to take those items back off again, I will get 5 first, and then I will get 1. And I can't get them the other way around. And that's why it's called a stack, because they stack up and you pull them off. And as I say, it's called a last in, first out stack. That's the sort of terminology for it, because it explains how it works. Now, rather than using our temporary load and save variables here, what we can do is we can use the stack instead to store A and to get it back. And the commands we use are called push, to push a new item onto the stack, and pop, to kind of pop one off. So let's have a go and let's see what it does. So push AF will push the character the user has entered onto the stack, and then pop AF will bring it back. So that will now store the user's character and bring the user's character back. And then what we need to do here is the same thing again. Push AF and then pop AF. And what I'm going to do here is I'm going to put breakpoints on all of these here. So what we're going to do is we're going to see every stage within this program, but I'm not going to step through because we don't want to see what the print char commands do, because they'll run all kinds of crazy programs within the firmware. We don't want to see that, we don't care, but we do want to see how that stack works with these variables. So let's compile that. And we'll have another go. So we'll just clear our screen here and do call 8000 again. So the first command we're going to do is to wait for the character. And I'm going to press A. And now we're going to print the character. And now we're going to push A onto the stack. Now you'll see here A is currently equal to 61. And also F is the flags. That's things like the 0, the Z, the NC, the C that we mentioned the other week when we're doing if statements and things. They are stored in a kind of weird register called F, and A and F make up a 16-bit pair. You can't use them in the same way as HL, but when you push and pop them off the stack, F, the flags, comes with A as part of the functions of the Z80. So that's something to bear in mind. So anyway, we're going to push onto the stack. And here's the stack here on our screen. And you can see 6187 is now the top item on the stack. And of course, it doesn't affect the value in AF. AF doesn't reset or anything. It's just backed it up for later onto the stack. So let's carry on. And you'll see we've now loaded that semicolon symbol. And then we're running the print jar. The screen is running a little bit behind here because the screen refreshes as if it's a TV. So that's why we haven't seen that appear just yet. So now we're doing another push, and this time we're pushing 3B87 on the stack. And you'll see 3B87 is now at the top of the stack, and the next item down is that one we pushed just a moment ago, which is the letter A that the user typed in. So now we're loading the X into A and printing that X. And now we've got a pop command. So what we're going to do is we're going to go back to the stack and we're going to pull back that value. And if you just watch, we've got currently 3B87 in the stack. AF is now 3B87, and the important thing to note is 3B87 has gone from the stack. Because we popped it off, it's kind of sprung away and has disappeared from the stack. And that's the other important thing to see. So now we're going to carry on. And we're going to pop the remaining one item off the stack. And there's an important reason why it's the only one remaining item, which is the letter A. And then we're going to print it. And you can see the functionality is identical to the original program. Now, you're probably thinking, well, that was all a bit weird. Why would I do that? Well, let's have a look. The program is now 801C in length. And if you look before, it was 8024. So if I just get my calculator up. So it was 36 bytes. And it's now 28. You see, we've saved quite a lot of space there, and this is a tiny, tiny little program. So, you know, we can save 8 bytes here and there by using the stack, because a stack command is just 1 byte. A push or a pop is 1 byte. An LD command is 3. And that means a couple of things. Not only is it the space the program takes up, but push and pop are very, very fast. They're the fastest memory access commands that the Z80 offers. So anytime you can use them, you should use them. And especially for temporary storage like this, if you've got no reason to save it long term, if you just need it within that function, you should always use the stack. It's the fastest way of doing these kind of temporary storage of memory. So there we go. Now, there is another rather unusual thing about the stack that I want to show you. So let's just take all these breakpoints off for a moment. Now I'm going to show you a very small program that isn't actually in the sources, because It's explained, but it's not shown like this. So what I'm going to do is I'm going to create a test function, and it's just going to have a ret, and it's going to have a, well, it doesn't really matter, kind of a print char, say. And we'll put one here as well, and then we're going to do a call, and call is like go sub in BASIC. It runs a function and then returns back. So we're going to do a call to the command test, and we're going to put a breakpoint here, so we see before test runs, and here, so we see as test is running, and then here, so we can see after test runs. So test is at memory location 8009. The call to test is at 8005. Now we're just going to take a note of that because that's going to be interesting to us in a moment. 8005. Let's just get this out of the way over here. So let's do our call of 8000. So take a look at the stack here. And this is how the stack is as our program starts. There's always going to be things on the stack because the stack is used by the firmware of the Amstrad anyway. But the important thing to note here is you're probably looking at this program and saying, well, this program doesn't use the stack. There's no push commands, there's no pop commands. It doesn't use the stack. So why are we looking at the stack? Well, let's have a look what happens as we step through this program. So we're about to call the test routine. And if you look at the B9A2 at the top of the stack, so, oh, the stack has changed. And what's the address in the stack? Well, if you remember, I sort of said 8005 was that call command, and 8008 is the return command. Why has the address of the return command been pushed onto the stack? Well, I'll explain. It's very simple. When you do a call in assembly, the address that is going to be run when the return occurs is pushed onto the stack. And when you return, an address is taken off the stack and is put as the next command the assembler, the Z80 will run, which is effectively the program counter. And you've kind of got to remember that the Z80 doesn't really have any magic resources it's hiding from you. Everything that it can do is shown to you on this screen. It's not really got any other registers. It hasn't got any memory of its own. So when it's remembering when you call subroutines, when you call firmware functions, the only place it has to remember where it needs to go back to once it's finished that is actually the resources you're seeing, and it uses the stack. And this is sort of important for a couple of reasons. Now we'll just carry on, and I'll just show you, just prove to you, shall we say, that that's true. So you can see here we're currently at 8009, and the address 8008 is on the stack. And here we go. The return just occurred, and now 8008 has gone off the stack, and program counter is 8008, and that's what the return function did. And actually, if we step through now, you will see B9A2. We will just do an F7 here, and that B9A2 has gone, and it's been loaded into the program counter. So what does this mean? Well, it's a bit odd, but I will explain it to you. As I say, when you do a call command, so when I do call test, you could actually think of that as push PC, PC being the program counter, the command the assembler is actually going to run, or actually, I suppose that could be said as next program counter, but we'll call it. So it pushes the program counter, and then it jumps to the label. And when you do a return, you're effectively doing pop program counter. That's kind of what those commands are. That's kind of what the call does, and that is literally how it works within the Z80. And there's a really important reason why you need to know that, because there is something you cannot do, and I will show you what it is. I'll show you how to crash your machine, shall we say. So if I will take that up, and what I'm going to do is I'm going to put a push AF here, and I'm putting these little tabs in so you can see where the matching pop is. And I'm going to put a pop here. And so what we're going to do is we're going to load the semicolon into A. We're going to push it into the stack. We're going to call test. We're then going to pop AF off the stack. And we're going to call print char. Now I don't advise this at home, and you'll see why. So let's compile it. And let's have a look what actually happens. So I should have put a few more breakpoints in there, but never mind. So we've loaded our A with 3B, and you can see it's been pushed onto the stack there, along with the flags, which we don't really care about. And then we call test. So let's do that. So test has now been called, but that means that 8006 has also been pushed on the stack. Now when we do our pop command, it pulls the top thing off the stack. It doesn't care whether what was pushed on it. A push AF can be popped off by a pop DE. It really doesn't care. And because we've done that call, and because the Z80 has pushed the program counter onto the stack, the pop command is now going to pull off the program counter and not the semicolon that we had kind of intended it to do. So what will happen next? Well, when we do our call, what will actually be shown on screen is the ASCII representation of the address we were going to return to. Now that's not too bad, but what happens here is quite bad, because now that the pop command has taken the return address, when we return, we are going to return to the semicolon with the flags, and that's going to be a totally random address in the system. And look what we've hit a no op, so that's a no operation, doesn't do anything. And actually what we've ended up with, coincidentally, and it is really coincidentally, is we've ended up with an infinite loop. But we could easily have ended up with running part of the firmware. We could have crashed our machine. In theory, we could even have ended up reformatting a disk or something. Anything. When you do that kind of thing, anything can happen. So the important thing to know from this is that push and pop commands within a called function have to match, because the call or the return will use the stack. So the stack needs to be in the same state as when the call started, unless you really know what you're doing. Now that's not the case with a jump, because a jump command does not use the stack. So if I change my little program here to jump test instead of call, and I'm going to put DI and halt here. And what DI halt means is it will. I'm going to explain those commands later, but it's just a sort of quick, dirty way of stopping execution. So if the Z80 ever runs these commands, the machine would crash, but it's never going to, and I will show you why. So let's do our assemble here, and let's do our call again. So we're pushing AF, which is our 3B68, which is the semicolon, and then we're jumping to test. Now we're jumping this time, not calling, and because jump does not use the stack, when we get here, our semicolon is still at the top of the stack. Now I just need to put a little breakpoint here, because now we get back to our return command, and we jumped here, not called. So rather than returning to the address below the jump, well, jump doesn't work like that. So when it returns, it will actually finish the program and go back to basic. And we can just prove that, because everything works fine. Whereas if you did return to here, the DI halt would have crashed the Z80. So that's a little thing. And also, if you never need to come back, if you've got no more commands to do, if we just turn this into a viable program here by getting this push pop. If you were going to do this and you were going to call test and test was going to return, and then all you were going to do after that call is return to basic or return to whatever had called this subroutine, you can save a byte here, get rid of that and change that to a jump. Functionality is exactly the same. You've saved 1 byte off your program code, and also you've saved the Z80 a little bit of extra work, because why would it come back just to return anyway? So if you don't understand that, just don't worry about it. It's maybe a little bit advanced, but if you're trying to squeeze your code down as fast and as small as possible, you want to do that. But the important thing you must know at this stage is if you're writing a program, I'll just get the proper program back in. I'll just cut and paste it from my source code here. If you're writing a function that you're calling and returning, you've got to make sure the pushes and the pops match each other, and that's why I've tabbed them in here. And if you look at the sort of website, my website, I've actually coloured them as well, so you can see this pop will get the data this pushed, this pop will get the data this pushed. So hopefully that will make it clear to you how to do it. And if you get them mixed up, as I said, you can change push AF, you can have push AF and pop DE. That works just fine, but you have to push them on and pop them off and have the right number. If you push more on than you pop off, you'll end up crashing when your return happens. If you pop more off than you pushed on, you're probably going to end up crashing when your return happens. It's always, you should really try and make them match, at least in the early days. You can do some really clever things with push and pop if you know what you're doing. We're going to do a simple little one in a moment, but generally speaking, at least in the early days, make it all match, keep it all neat. And I think some assemblers don't like it, but with Win8 you can tab in here and have these kind of tree structures so you can see your matching pushes and pops, and I do that and it helps me make fewer mistakes. So anyway, we're going to move on to our second little program here. I'm just going to leave this one up here because it's not going to do any harm to us, and we're going to write our new program. So this one's going to start as org8100, and what we're going to do is we're going to load HL with an address which we're going to label introduction, and then we're going to do call print string, which is a function we're going to write but we haven't written it yet, and then we're going to do call new line, which is also a function we're going to write. We'll learn how to do that in a moment. And then we're going to load HL with the address of something we're going to call message, and then we're going to call print string again. Okay, and then we're going to return. And as I just said, this is kind of inefficient. This could be a jump and this could be removed, but these are example programs, so I'm trying to make them a little bit clearer. I'm not trying to save every byte we could. It's not needed for these examples. So let's create this print string routine. So what we're going to do is we're going to use our print char routine that the Amstrad firmware has provided us, and we're going to use it to print a whole string. So we're going to load A from the memory address contained in HL. Now when we run this program, HL is going to point to a string. So actually, let me bring the string in for you so you can see in advance what we're actually coding to work with. So here's one of our strings. So the string is this is introduction, which we load into HL, and then DB defines a series of bytes. And as I said before, although these are letters, the assembler will convert them to the equivalent ASCII characters. So these will all end in bytes. And then at the end of this string, I've put a byte value 255, which is the last possible ASCII character. Nothing uses it. Nothing really uses above 128. So 255 is a good, safe byte to use, and I'm using that as a marker for the end of the string. So let's carry on with our print string command. So as I just said, I'm going to check if the byte we're currently reading is the end of a string, and if it is, we're going to return. So if the difference between 255 and 8 is 0, return. That ends the string. The string printing must be done at that point. If it's not, we're going to increase HL so that we move to the next location in the string, and then what we're going to do is call print char. And at this point, I will point something out. I know, because I've checked the documentation, that print char does not affect any of the registers in the Z80. So we're pushing A into it, and B, C, and HL, and various other things we may be using. According to the documentation, print char does not change any of those. If the print char routine altered HL, this program would not work. But because I know it doesn't, we're fine. But that, you can't rely on that. If you're using if you're using firmware functions, you need to check the documentation of your hardware and make sure how they affect the other registers, because in a lot of cases it could alter the values in them. If you need to be safe, just push the ones you need to be the same. So if I knew printchar broke HL, I can do push HL here and then pop HL here, and that will protect HL from being altered by the printchar routine. But as I say, I know it's okay, which is why this program will work. So we're going to jump to our print screen, and then we need a message, and the message is going to be Z80 is awesome, which is true. And then we need a new line command, because we've used our new line command here. And let's make a start on that. So new line is going to be very simple. All we do is load a, 13, and then we do call print char, and then we do load a, 10, and then we call print char, and then return. And as I said before, I will just show you, because we're calling and then immediately returning, we can just do that, and that's the same thing. Saves a little bit of memory, saves a little bit of speed. So there we go. Sorry about that, I just strange pause in my software there. Okay, so we'll do call 8100, and the message, the first line prints thought of the day, gets the character 255 and the print char end. Then the new line command calls and starts the new line, and then it prints Z80 is awesome. Now, why did we do CHR13 followed by CHR10? Well, this is an old typewriter kind of thing. CHR13 meant carriage return, which is where the sort of mechanical head moved back to the start, and then 10 was new line, and I suppose you could think of a printer, and the new line would roll the paper up and it moves the cursor down. Now, depending on the system you're programming for, the commands you need to use here are different. On the Amstrad CPC, it's character 13, character 10. On the MSX, it's character 13, character 10. On the ZX Spectrum, I think it's only character 13. It's certainly not both. And if you're programming for the TIE calculator, it's neither. They don't do anything. And it's a totally different function you have to call for the new line. And that's why I've created this new line function. By doing this myself in my own little function, rather than embedding it in, you could embed the 13 and the 10. I could put them here, but that would only work on the Amstrad CPC. By creating a separate function, it allows me more easy portability to other 8-bit systems, because all I need to do is reprogram that new line command to do whatever the hardware I'm working on needs to do to have a new line printed, and I'm sorted. And that's very true of the print string. Some of the systems may have an easier way of printing a string to screen, but how they define the end of a string, and some of them may not have any such function. So by writing it myself, it's only a small little thing. By doing it myself, I'm guaranteed portability across other systems. So that's why we're doing that. Now, we're going to have a little bit of a joke with this. Now, you've seen before we use these definitions where we're defining print char and things, but there is another way you can use definitions, and this is for assembler directives. And so what I'm going to do is I'm going to create a kind of meaningless variable called think positive, and I'm going to define it to 1. And then what I can do here is, so just trying to find my code here, and then we can do a command called IFDEF. Now you'll notice this has kind of gone a red colour in the same way as the load commands and things. And I'm just going to paste in my alternate message here, which is a gratuitous slur on the Commodore 64. I apologise for that, Commodore 64 people. So, what have we done here? Well, this is processed by the assembler, not by the Z80. So the assembler says, well, if think positive is defined, if def means if defined, then print Z80 is awesome. If it's not defined, else print 6510 sucks. And by saying think positive equals 1 here, we have defined it. So 1, 2, 144, anything here is a definition. So when we run this like this, and do call 8100, the thought is how awesome the Z80 is. But if I've put a semicolon there, which is a rem statement. So if I as I compiled it again there, if I do call 8100, the thought of the day is that the 6510 sucks because we're not thinking positive. Well, you're probably thinking, well, that's pretty immature and pretty pointless, but it's not. It's a good example of something quite important. Now, what we've got here, we've got a single Z80 program in assembly language, and by changing just that one line at the top, we've actually changed the bytes that the assembler produces. You'll see here there's the message 6510 sucks, but nowhere in the bytes that are passed to the Amstrad CPC is the message Z80 is awesome. It's not physically in the program, and that's because the assembler never compiled it. Now, this has allowed us to create two different versions of the program that do not contain any wasted space by that unused message. And more importantly, we can do this to create multiple versions of the same program that will be run on different systems. If you look at the code that my program, that my Chibi Akima's game uses, I have compiler definitions at the start of the program of def build CPC and def build ZXS and all kinds of things. And by enabling and disabling those, I can actually recompile my entire game for a completely different hardware platform, because the parts that are relevant to that platform or aren't relevant to that platform are disabled and enabled by these IFDEF and IFDEF with not defined statements. And I can have one piece of code that can be sort of switched on, bits can be switched on and off to create these whole different versions of the game, and that makes developing the game possible. But it means that I can develop one game, one level, and then I can compile that one level for not only three different platforms, but also 3 different disk systems in the case of the Spectrum, and even multiple languages, because I can switch, just like we switch Z80 is awesome and 6510 sucks, just depending on think positive. Well, this could be IFDEF build French, and then 2 translations, or it could be build CPC and then this definition of new line and build Thai for the Thai calculator and an alternate definition. And this isn't a theoretical example. I actually am working on a set of development samples for Hello World that will compile onto 5 different systems, and the only thing you need to change is the build definition at the start. So that's something I'll show you in a little while maybe. So that's as I say, very, very powerful. It may look a little bit silly at the moment, but it can be used for far more than just printing silly messages on the screen. Now, just to reiterate, the one that isn't compiled, if think positive is defined, this is compiled. If it's not, this is compiled. Now you'll see that the label message is used in both of these cases, and you can't use a label more than once within a program. But because the compiler definition only allows one of these 2 to be compiled, even though you see it on screen twice, only one will ever actually be compiled by the assembler. So you see them both in the code, but the compiled code only contains 1. So we've not broken the rule of redefining message. So again, just trying to explain there the fact that the compiler directive is separating the defined code so that there is no duplication and it doesn't end up in the memory. Okay, so we've got plenty more to learn today. So let's make a start again with a new program. So all of these programs are sharing little bits of code, and it doesn't matter where we put our code in here, so long as we don't delete anything. So the next one is going to be at 8200, and we're going to be using another unusual function of the Z80, which is indirect registers. Now, there will be cases where we want to specify an address to some memory, but rather than, if you think of our sort of temp example before, there may be times when we actually want to specify, we actually want to use one function and specify different addresses different times. Well, what does that mean? Well, we'll have a look and let's explain it. So what we're going to do is we're going to create a command called do brackets. We're not going to create it like that because it won't work. So do brackets. And And what we're going to do is we're going to load A from square bracket, my sloppy programming here, from square brackets, and then we're going to do call print char. And what's that going to do? Well, it's going to print the first character from square brackets onto screen. Well, that's pretty straightforward. And then we're going to do something a little bit odd here. We're going to do call, and we're going to define a function called do call DE, and we're going to develop that in a moment. So bear with me on that, please. And then what we're going to do next is I'll just copy paste that here, and we're going to load the second square bracket, so that will read from here, and we're going to print that on screen, and then we're going to return. Again, as I said, I could have made that into a jump and remove that last return, but I'm not going to. So, okay. And here, what we're going to do is we're going to load the message into HL. We're going to load DE with print string. And if you remember, print string is our function that prints a string. You might be confused by what we're doing here, but we'll get to it, don't worry. And then we're going to do call do brackets. So do brackets will run. It will print the first square bracket. It will then do this call DE, and we will define that now. Now you may remember I said earlier about how the call and return commands actually use the stack, and we can do some slightly mischievous things with it if we know what we're doing. Now what we're going to do here is we're going to do push DE, and then we're going to do return. Now I said that there should always be a matching push and a pop when you do these calls and when you do a return, but what we're doing here is we're tricking the system. When we push DE onto the stack, it will appear as a piece of data. When we return, that DE will be popped off the stack and will be put as the next command that's run. And that's why we're calling this do call DE. What calling this function does is effectively it does that. It calls the memory address DE, but there is no such command as call DE. I'm going to show that to you if I do assemble. Oh dear, bad expression. Can't do that, but what we can do is we can create the equivalent, which is push DE onto the stack and then return, which moves the program counter to whatever was in DE, and because this is a call in its own right, it has the resulting effect of call DE, because when the return that would have happened here occurs, it will end up here. I probably explained that quite poorly, but just trust me, this will have the effect of calling the memory address DE and then carrying on with our square brackets. And it's very easy to prove that. So let's compile. And let's do call 8200. So we've got 6510 sucks in square brackets. Now, that's okay. That's a thing. I don't know if it's particularly useful, but it is going to be useful for teaching you about indirect registers, because you noticed here I've got these curly brackets. What I actually want to do is I want to print the message in square brackets, and then I want to print it in curly brackets. Well, how can I do that? Well, one option certainly would be to use to use maybe BC here and then inc BC, but I'm actually going to show you how to do it with the indirect registers. And what an indirect register is you've got two on the Z80, IX and IY, and what we're going to do is load IX with the memory address square brackets, and then we're going to change this to IX plus 0, and we're going to change this to IX plus 1. And what I've just swapped there is functionally identical. It will do the exact same job. It will read A from the address in IX without plus 0, so just IX effectively, and then it will read the address from IX plus 1. And you should notice this is not changing the value in IX. IX is exactly the same here. And so if we compile that, you'll see it works exactly the same. And the sort of trick with this is we can now copy all of this load our curly brackets, assemble again. Oh, sorry, I just accidentally stopped the assembly. And we do call 8200. And you'll see that our one function can do both kinds of curly brackets because we're using that IX. As I said, you could use BC in this case, but IX is and IY, they both work identically. IX and IY are far more powerful than HL, using HL and BC, because you don't need to increase and decrease. If I could have done this as load BC and inc BC, and BC here as well, that would have worked, but I can do all kinds of crazy things here, and I don't need to do any inks and decks. That's 1, 2, 3, 4, 5, 6, 7, 8. So if I now put this to, I think that's going to be 9. So I'm too impatient here. So you'll see here, I've managed to load in the address from 9 just by putting +9 there. And if I was using BC or something for that, I would have needed to add 9 to BC or do 9 inc commands. But also I can specify any random number within that range in any order without changing the value of IX. So you can see here I can now run it again. And you can see we've now got the square bracket, the 10th character along. This is just picking up some random garbage because I've not made this long enough. I really should have made that longer. And then it's getting the character from 0 again. And this is the point, you can use them randomly, and it's not even just load commands. You can do all. There's some really powerful commands that allow you to use IX. Another thing to consider is if you don't want to use these, IX is actually made up of 2 parts, IXH and IXL, and you can use those as 8-bit registers as well. They're a little bit slower, they're not as good as the normal ones, but if you don't want to use push pop to free up some memory, if you don't want to use declared memory addresses and load commands, you can use IXH, IXL, IYH, IYL as temporary stores for maybe loop counters and things. I use them quite a lot. They do give you a little bit of advantage, but they are a lot slower. So don't use them unless you need to, and unless you've worked out this is definitely going to be faster in the long run. But it's worth remembering them. So that's a bit of a weird example of how to use the IX register. I just wanted to show it very briefly. I don't want to program in a lot of code to show you how to use it. But if you're thinking, well, it seems pretty useless, I won't bother, I'll just explain the killer use for it in my game, my Chibi-Akins game. Chibi-Akins is a 2-player game, and there is a routine called handle player, which is the entire player driver. It does everything with players. It draws the player on the screen, it calculates the whether the player can shoot, it reads the player's input, it draws the player's health. Everything is done with this, and the way it works is there is a 16-byte player status array in memory, and what I do is I load IX with the address of that memory, call the player handle, I then load IX with the second player's address, call it again, and this one function does both routines. And because IX allows for this kind of random reading of the data relative to the start point, the start address that IX was, or IY was loaded with, it's really flexible for that kind of thing. So maybe if you don't understand it, don't worry about it too much for now, but just bear it in mind, because one day you'll probably think, oh, there must be some way I can make this work. And it might be that IX is going to help you make your code a bit more efficient, make it a bit easier to write, probably both. So yes, please bear it in mind. So that's how to use IX and IY for indirection. There is another thing I'm going to teach you. It's going to be the last thing today. And maybe if you think that IX thing was a bit nonsense, maybe this will convince you. So let's make a start on this last little program here. So we're going to do org and 8300, and then we're gonna, well, let's make a start. So what are we going to do? I'll explain what we're going to do next before I actually do it. We've been doing these calls, and we've always just done call 8300. to compile my code. That doesn't work. So we've been doing things like call and 8300. Now, if I put a breakpoint here, and what I want you to have a look at, let's use the copy command, copy that. You'll notice that A is 0 here, and you may think, well, that's probably just some garbage that has been left over from BASIC, but actually it's not. On that, and this is Amstrad CPC specific, but when you do a call, A is loaded with a very specific value, and the value is how many parameters that the basic call command had. You see, Amstrad CPC BASIC has a quite clever function where you can pass certain kinds of variable to your assembly program on the basic command line. So if I do call 8300, 1, you'll see that A is now 1. And then if I look at IX, you'll see that's BFFC. So I'll just copy that and I'll do go to. I'll actually do it in this bottom screen. So go to. And you'll see here that 0100. Now brace yourself, guys, because this is a bit tricky. I don't know if you remember, but I mentioned before that the Z80 loads data backwards. So when you pass a parameter in BASIC, or when you do anything with 16-bit numbers, because that's what it is, it's a 16-bit integer. When you pass effectively 0001, look at that. So when you pass 0001 into a 16-bit number, when it's stored in memory, it's split into 2 bytes, which makes sense because it's 8-bit, but that's loaded backwards. So 01 comes first and 00 comes second. It's a bit annoying, but yeah. It's called Little Endian, END. It's apparently some kind of pun on the word end, and which end is big and little. I don't know. It seems very strange to me, but it's nothing to do with Indians. It's Endian. So yeah, you just need to remember, if you're starting to do things with the memory itself, or you're doing self-modifying code, you need to remember which byte is which, because I make the mistake very often and my self-modifying code doesn't work, or I end up corrupting my screen memory and things. So yeah, it's important to remember. And that's, you're not seeing 0, 1, 1, 0, 1, 0, 0 here, you're seeing 0, 0, 0, 1 here. So that is those 2 bytes there are actually the one we passed here. And let's just do. I'll give a really easy example. 321 hexadecimal 3210. Hexadecimal 3210. Now you can't rely on it always being at the same location, so you would actually need to see IX, because IX, when you do these basic calls, IX, that indirect register, is actually passed with the location where BASIC decided to store the first of the variables that were handed on. I think they actually come out in reverse order, but we're only going to use one today. So let's make a start on it. So the first thing we're going to do is we're going to do compare 1, and what that does is it compares A with 1, and if the user only passed one variable, like this example above, like this example on screen here, then A will be 1, and that's what we're expecting. But if the user hasn't done what we expected, then we're going to do a jump non-zero, because the difference is not 0, the difference between 1 and what was in A. And then we're going to jump to show usage, because we're going to be kind and give the user a help file. And then what we're going to do is going to load A, comma, and we're going to load an AND symbol. And we're going to print that to screen. And in CPC BASIC is, of course, the hexadecimal symbol, and maybe that will give you a clue what we're going to do. So what we're going to do next is we're going to load A with IX plus 1, which is the high, as I said, it's little endian, so the high part is at plus 1 and the low part is at plus 0. So we're loading the high part first, and then we're going to do OR A, which, if you remember from last time, OR A is the equivalent of CP0, but it's smaller and faster. So we'll put CP0 in there just in case people missed or forgot the last lesson. And then we've mentioned jumps before, but you can do these conditions with calls in just the same way. So if A is non-zero, if the difference between A and 0 is non-zero, which effectively means if A is non-zero, then we're going to call a function we're going to write called show hex. And there's no prize for guessing what show hex is going to do. And then we're going to load the smaller part, so which is ix plus 0. And then we're just going to call that even. We're going to just show that even if it is 0. And I think that'll make sense once you see it on screen. So there we go. So we need to have a message to show the user, and that's what it's going to be, telling the user how to use the program. I'm typing that in. And so we need show. And all we do here is we're going to load HL with the address of our message. And then we're going to do call print string. Okay, and then now what we need is we need our show hex command, which is a little bit complex, unfortunately, but I think it's worth you seeing. So when I've done a video on how to convert hexadecimal to decimal and how they work, and the way you do it is you divide each. If you think of a hexadecimal digit as being 0 to F, you divide each digit by the value of its column by its column value. So the first digit, if it in a hexadecimal byte, if it was 1, would be worth 16. So we're going to divide by 16. So what we're going to do is we're going to load B with 16, and then we're going to call mathdiv, and this is a function we're going to write in just a moment, and it's not the same division function as last time. This one's a little bit more advanced, so we're going to have to use this new one. Now mathdiv is going to return a remainder in A. It's going to work out how many 16s there are in the accumulator, and it's going to return that value in C, but it's going to return the amount. If there's 8 remaining, it's going to store that in A, and we want that in we want that for our second character. So we're going to do push AF because we want that A later, and we'll pop it. I'm going to put that pop AF in there just so I don't forget it and end up crashing the program. And we'll do load A, C, which is C is the result that our mathdiv will give us, and then we're going to do call print hex jar, and that's another program we're going to write. And what that does is it takes a value from 0 to 16 and it converts it to 0 to F, which is our hexadecimal characters. And then our final command is going to be another call print hex jar, because this, when we've popped it, this will be from 0 to 15. So that's all done. That's all we need to do, and then we need to return. And then our final command here is print hex jar. And what we do here is we do CP10 and JRC hex jar not A to F. I shall explain this in a moment. And we add 7 here. And here we add 48. And then here we're going to use a jump to print jar, and as I said before, that means it's not going to return, so that's effectively the end of the function. So what does all this mean? Well, if you remember from last time, I said that I kind of think of C as chibi. If the accumulator is smaller than 10, then we're going to jump to this not A to F, because A is 10, it's smaller than 10, so we're not going to do that. And so we jump straight to here, and that adds 48. 48, if I just get my sort of list up here, 48 is the character 0, you see. And so what that does is it converts a 0 in the accumulator to an ASCII 0. And what this bit does, which is only gets called if the value is over 10, is 10 or more, is it adds 7. And the reason it adds 7 is that's how much you need to add to the 48 to get you to the A. Sorry, not from 48, to get you from 9 to A, so that 10, instead of printing a colon, will print a letter A, and 15 would print an F, and we don't need anything higher than that because hexadecimal doesn't use anything higher. So that effectively, that little routine there effectively converts 0 to 15 from 0 to 15 to 0 to F, and that's our hexadecimal character range. So that's what we need there. And now all we need now is a new math div routine that's a bit better than last week's, because this one needs to give us remainders. So let's give it a go. Now, first thing we're going to do is we're going to compare to A to 0, and if it is 0, then we're just going to return. Now, the next thing we're going to do is we're going to load C, which is our result counter with 0. So we've got a start point, and then we're going to do a command called math div again. And what we're going to do is we're going to subtract B, because if you remember, B is the number we're dividing by. And subtract B, of course, subtracts from the accumulator, and the accumulator is the value we want, is our hex digit that we want to divide by. So there's our subtract B, and if we were able to subtract B, then we want to increase our count by 1, and C is going to be our count. So we do inc C, and then we do jump in C, comma math div again. What does this do? Well, when we subtract B, if we go below 0, then the carry flag will be set, and so we won't want to carry on. But if we haven't, the carry is not set, no carry, we want to keep subtracting B until that happens. When it does happen, we've gone below 0, and we need to get back from that to get the correct value. So what we do is we add B, that brings our value back from 0 up to the correct amount, and that's in the accumulator. So that's the remainder. It'll always be less than 16 in this case, because because it wasn't divisible by 16. And then what we do is do dex C, and that's, as I mentioned last week, is because the inc C here is before the comparison. That's just the way this this works. So, and then we return. Let's give it a compile. No errors. How's my typing doing? So if we do call and 8300. And I'm going to do a silly example here, and I'm going to do 3210 in hexadecimal. Now, if it comes back with an hexadecimal 3210, you can be pretty sure I've done it right. And if it doesn't, you can be pretty sure I've done it wrong. Breakpoint, we didn't want that. 3210. So that's a good start. So let's try again. FFE9. So you can see it seems to be working, but of course that's not much of a test. Let's do call and 8300, 12345, and it comes up with 3039. Well, let's get our hexadecimal calculator out. Let's test if it's done that right. 3039, 12345. So there we go. What we've got here is we've got a basic command which is calling an assembly language program, and it's passing a variable straight away to that assembly language program. The assembly language program is processing it and printing it back to the screen. Now, as I've said, this trick of passing variables is a bit of a CPC exclusive. The MSX does have a command where you can pass a single variable. If you want to see about that, please look in the basic documentation. But you can only pass one variable on the MSX, whereas on the Amstrad CPC you can pass an awful lot. I don't believe it's possible on the Spectrum. I think it seems to be one where the Amstrad CPC wins. If you're not interested in Amstrad CPC, please just consider this a good example of how you can use the IX indirect register. But if you need to do this kind of thing and you can't, and you're not using the Amstrad, then what I'd suggest is you go back to the more simple routine that I showed you last week, which is using peek and poke to pass data in and out of your assembly language, because that will work on absolutely any system that's got peek or poke. So that's a really great thing to bear in mind. The other thing I would say is I've shown you now how to do various kinds of call from BASIC to assembler. And what I want you to consider is, if you're starting out writing your own little game or your own little whatever, then please think about the possibility of only writing the most complex parts in assembly and keeping the easy stuff in BASIC to give yourself an easy start and things. What you can do, and what I actually did with my Chibi Ackerman's game, is you can write your sprite routines in assembly. You can write your input routines in BASIC. You can write maybe your game logic, just depends how complex things are in BASIC. Just use assembly for the tough bits. Get the bits that you need to think about. You need to do a bit of trial and error in BASIC, where you're not going to get the nasty crashes. if you get to a point where the basic is where the game is functional and you're thinking, well, okay, it works, but it's too slow, which is where Chibi Akinas was, you can then take that basic as a kind of template, write the same functions in assembly, knowing you've worked out all the tough, is this possible, does this work, how do I want to make it work, what does it look like. You got that worked out in the basic, and now you can just work out the actual tough stuff of the assembly coding, where you do risk the crashes if you make mistakes. So please don't feel ashamed that you're writing half your game in basic or 2/3 of your game in basic. If you can, an assembly sprite routine is very, very fast. An assembly music player is really good, and it can make what would otherwise be a basic program plus just a little bit better. And the important thing is you're making things that you enjoy, you're making things that are playable and that other people can enjoy. So if that means making half of your thing in basic, well, just go ahead and do it. There's no shame in it. It's brilliant. And as I say, you can then start building your assembly skills using your basic skills as a foundation. So definitely consider doing that. So there we go. I think we've got through quite a lot of stuff today. I apologise for one thing, the scrappy nature of the code here. Please go onto my website. You can see there's a text documentation describing all of these programs, and also you can download this, which is the pre-programmed version, which you can download. You can just, if it's too much, if there's been too much today, if you've typed in you can't get it working, just download it, compile it. You can do all of the examples exactly as I've shown you today, and you can just have a go with them and tweak them whatever you want. Now, as I said as well, if it is perfectly possible to reprogram all of these examples today onto other 8-bit systems, all you need to do is replace the print char and the wait char routines, and replace that new line command if you need to for your system, and these should be compilable on other systems, with the exception of the indirect registers and the getting the variables from basic. But there we go. Right, well, I think that's the end of this week's lesson. If you've liked it, please let me know. If you want to see more videos, if you want to see better videos, please consider backing me on Patreon. This week's really took me a long time to do. I want to keep making them as good, and if possible I want to make them better, but it's very hard to find the time. So yeah, please let me know if you like it. Well, I think we'll leave it here, and tune in next week if I can. I'll try and get you another video. Thanks for watching. Goodbye now.